Hello everyone, you're tuned in to today's PIR live event, and I'm your host for today, Scott Jones. Our guest today is Dr. Guido Van Marle, Associate Professor in the Departments of Microbiology, Immunology, and Infectious Diseases at the University of Calgary. So welcome to the PIR live event today, Dr. Van Marle. Before we get started, I'd also like to welcome today's viewers watching the live stream. It's great to have you with us again today. Remember that throughout the broadcast, you can tweet us any questions that you might have using the hashtag AskPIR. If there's room in your tweet, please include your name, school, or city so that we can give you a shout out. So I look forward to getting to some of those questions through Twitter, but first I'll turn it over to Dr. Van Marle to start us off. So Dr. Van Marle, can you please introduce us to virology and your work on HIV, hepatitis B, and West Nile?
Good morning here if you're out on the western side, or good afternoon for you out east. Yes, I'm a virologist at the Cummings School of Medicine here at the University of Calgary, and I study HIV, West Nile virus, as well as hepatitis B. Primarily HIV and hepatitis B virus infections. I study how the virus replicates, how they cause disease, how they mutate, so they escape vaccines, as well as the therapies that we have. So today being World AIDS Day, I'm going to probably address a little bit more on HIV, but a lot of things that apply to HIV or human immunodeficiency virus also applies to other viruses. One of the things that we work on is how does the virus change and how does it evolve? I hope you're familiar with HIV to a certain extent. It's human immunodeficiency virus. It's the virus that causes AIDS, or acquired immunodeficiency syndrome. It's quite a mouthful, but it means that the virus destroys the immune system of the infected individual and then causes disease, because she becomes susceptible to all kinds of other infections that in the end you will succumb to infections that normal, healthy, uninfected individual or an unaffected individual, so a person who doesn't have AIDS, would normally be able to fight off. So we talk about HIV AIDS, so people who are infected with HIV, we call them HIV infected, and somebody who has HIV and AIDS means that is the person who is HIV infected and has the immune deficiency, or his immune system is no longer working. So when we talk about AIDS, we specifically talk about HIV AIDS, because there's other ways you can acquire an immune deficiency. So I'm just going to tell you a little bit more about HIV and then we probably open it up with some questions from the audience. That's okay with you, Scott?
Yep, that sounds great.
Okay, so if we talk about HIV, we have about 37 million people worldwide infected with it. Not everybody have AIDS. About 2 million infections each year still, new infections, people who are newly infected worldwide, and about 1 million people die from HIV infection / AIDS, or the complications associated with HIV infection. Most of those people probably die from opportunistic infections, so other infections, so it's like TB, tuberculosis, malaria, even hepatitis B virus. So that's the main cause of death in those patients. It's a sexually transmitted disease, so it gets transmitted via sexual contact or blood contact, so people injecting drugs or sharing needles, so heroin users that share needles would be, and one is infected, you could infect another individual, or if you would use dirty needles to administer drugs or medications or vaccines, that would be another way of getting infected, or through blood transfusions. We all heard about Ebola, where you have to isolate people really seriously to not get exposed to their bodily fluids. With HIV, it's less infections, like from you can sit next to somebody, you can work with him, shake his hand, nothing wrong with that. You can, and that's probably also the reason why it's easy to get infected through sexual transmission, because after infection you might feel a little bit sick, but then you go through a relatively long asymptomatic phase. So a person doesn't get sick, doesn't know he's sick, doesn't know he's infected, he's not really sick, but the virus hides away in other parts of the body and basically chews away at your immune system till at a certain time point your immune system drops below a particular number of cells in order to be still functional, and you will become immune compromised, or basically immune deficient, so your immune system doesn't work, and that's when we talk about HIV/AIDS. What happens then too, at that moment in time, a person will also increase the amount of virus in its bloodstream, will go up quite considerably, which also leads to even a worsening of the disease. HIV destroys cells of the immune system, so it infects cells of the immune system. And by infecting those immune system cells, when it starts to multiply or replicate, the virus destroys those cells. That contributes to destroying your immune system. But actually, in the process of those cells dying, a lot of uninfected cells also die. So actually, more immune cells are dying than actually are infected by HIV. So the fact that HIV destroys the immune system, not necessarily due to the fact that it infects immune cells and destroys them. It's actually a lot of what we call bystander effects. So actually, side effects of like those cells dying, all kinds of signals gets released from the cells and the immune cells die. And actually, during the asymptomatic phase, that happens in other parts of the body, sort of hidden away from us to clearly observe. So when we took a look at the blood, you have enough immune cells, but in these other compartments, in other tissues in the body where there are a lot of immune cells, the virus is replicating and eating away at your immune cells. And then at a certain time point, your bone marrow, where the immune cells come from, the bulk of them, will not be able to keep up. And then with making new cells, because your immune system regenerates itself constantly, to adapt to new infections, and that's at a certain time can't keep up anymore, it can't control the virus anymore, and it basically destroys and you become immune deficient. We have no vaccine for HIV infection. There's no protective vaccine. There is some promising things about it. I will explain you a little bit later why that is the case. We do have antiviral therapy, so we have drugs that we can give patients that will block the virus from replicating. And when the virus, a virus gets into a cell, then hijacks the cell to make copies of its own genetic material and spits out new virus particles that then infect new cells. And there are several steps the virus needs to get in, then it sticks its genetic material in your chromosomes, in the genetic material of the cell, so you're as a human, and then can hide away there, but then uses uses the cell system to produce more copies of its own genetic material so that you get more virus particles. Now, that integration step, we have drugs for also the copying of the genetic material before it gets inserted into the host genetic material. We have drugs for that. We have drugs that prevent binding and entry, and then we have drugs that block the step when the virus comes out, and the virus actually has what we call maturate. So when it assembles it is sort of in a sort of unstructured form, which is non-infectious, and then enzymes within the virus chew that up and cleave that all and make little more organized Lego blocks for calling it like that, and then make the virus particle that then becomes infectious. So what we give HIV infected individuals to prevent replication and therefore disease progression, or if somebody shows up with HIV/AIDS, we give those drugs, we block viral replication, and then the person's immune system can hopefully recover again, and then you can stay healthy for a long time until the virus becomes resistant to those drugs. So we actually have to give the patient multiple drugs, not just one drug, because you've heard of antibiotic resistance with bacteria. You know, bacteria can become resistant to antibiotics. Viruses mutate too, and then can become resistant to the drugs that we use to block these several virus replication steps. So that it's almost like a key fitting in a lock, and then the virus is, let's say the virus is the lock, and the drug is the key, and then the virus changes a little bit so that the lock is slightly changed so that the key doesn't fit anymore, but the virus can still replicate. So if I give one drug of one type, that maybe blocks the copying of the genetic material, or the reverse transcriptase, so what we talk about is one of the enzymes. If that changes, then the drug doesn't fit anymore, it doesn't block that enzyme anymore, and the virus can replicate. And if I only give him one, it's easy for the virus to become resistant to one drug. But we make it harder by giving multiple different drugs, so different classes. So some of them that block the maturation or the virus particle formation, or now we have ones that are very good at blocking integration, so sticking that DNA in your genetic material of the cell. That is an essential step. And so if I give, for instance, 3 of those drugs, it becomes harder and harder for the virus to become resistant, because you have to change multiple different genes, which is a slower, lower chance, or it's harder for the virus to still become functional, or it replicates much, much less. So we can use these antiviral drugs to treat the patient, or basically keep their replication in bay, and by giving them multiple drugs, you can actually control the virus considerably, and it's harder for the virus to become resistant. It does happen still, so that's why we have different types of combinations of these drugs. So if you're resistant to one combination, we can keep you another, give you another, and then treat you. Of course, those drugs are expensive, so they're readily available like in Canada or in North America or in Europe, but in the developing countries, that's of course much harder. Now, some of those drugs have come off patent and have become cheaper, and so they've rolled out some of those combination therapies in like Africa, where sub-Saharan Africa, like we talked about, 37 million people infected, 25 million are in sub-Saharan Africa, so that was traditionally the most hard-hit area. If you take a look at the numbers of like 2000, in the year 2000, when we had those drugs available, those good combination therapies, very few people in Africa would ever get them. It would probably, if there were maybe 200,000 to 300,000 people treated with these antiviral drugs, it was only, let's say, in Europe or North America, not in Africa. And now we see that by quite some activities of the different governments and of the researchers in making the drugs cheaper, and all kinds of other prevention and education programs, we've been now able to actually treat 16 million people with these antiviral drugs worldwide. So it went from a small percentage to way more accessible, and a lot of course, here in Canada or the US, like 80% of the people who are HIV infected get antiviral therapy, same for Europe, but that used to be very small amount in Africa. It is now up to like 40%, so about half of the population. So HIV, we still a serious disease. We can't cure it. Even if we give those drugs, you don't get rid of the virus. We don't have a vaccine because the virus keeps changing a lot. So it's very hard to make a vaccine for a virus that changes a lot. So if to get rid of the virus or to protect against the virus, you make a vaccine, but that records one type of the virus. But if the virus has changed, you can still infect it. We remember, with every year with influenza, we need to have a new flu shot because the virus has changed. Now that happens with HIV too, but it works much, much faster, and actually that works in one individual. So while a flu vaccine may be protective for you because we can predict which virus is going to come, and your immune system is better adapted of recognizing that. With HIV, that's not the case, because the immune system recognizes HIV really well, even though it's hiding in the immune cells, but it keeps changing even in the infected individual. So if your immune system has learned how to recognize the virus, then the virus that is present in you has already changed, so the immune system doesn't recognize it anymore. And it's sort of like a battle, and you keep losing it. And most individuals in the world, that's the case. The virus keeps escaping, or we make antibodies, because vaccines induce antibodies. These antibodies are produced by the immune system that bind to the virus particle, and then the virus particle can get into the cell, and that's how you block infection. The problem is, you can make antibodies to virus particles that bind to the virus particles but don't block infection. And that's also what happens in a lot of HIV-infected individuals, that you make the wrong antibodies. Yes, they recognize the virus, but it doesn't block infection. Or a subset of all the antibodies that you make to HIV, only a few are good in blocking, and others don't. Some people are what we call long-term non-progressors, and those are people that are infected with HIV but don't develop AIDS. And one of the reasons they do it, or fighting the virus off, is by making the right antibodies every time the virus changes, or making an antibody that recognizes many, many different HIV variants that are present. So they are sort of very interesting individuals that we clearly study, because those are the people we want to study from. How do you make those antibodies? Because we know that everybody can make them, but somehow your immune system, in most people, start making those non-functional or not the really good ones. And then there are also other ways that people are protected, and that's just the way their genetic makeup is. And we want to figure out how those people fight their infection off, and then see how we can use that to develop a vaccine and a protective treatment, maybe. Because yes, we have good antiviral therapy, but you will have to take that the rest of your life. There's no evidence, clear evidence, that using those drugs, that over time you will lose the virus. The virus keeps hiding out in the infected individual. And so even though we might sort of curtail the new number of infections, like it used in 2000 was like 3 million infections every year. Now it's 2 million infections every year. We've reduced the deaths thanks to antiviral therapy from 2 million to 1 million each year. But you see, it's like 1 million people dying, 2 million people new infected. So every year, 1 million new infected individuals get added to those 37 million. If we can keep people giving more and more of those antiviral drugs and treat them, if you're treated, your amount of virus in your system goes down considerably, making it harder for you to infect another individual. Plus, with other education campaigns on safe sex practice, so uses of condoms, and also, clean needle programs, and testing the blood supplies carefully. In Canada, we do that really well with testing the blood, so it's a very small chance you ever will get it from a blood transfusion, because we have very good tests for that. But education and sort of prevention campaigns are very important there. So we've made a lot of progress since 2000 to now 2015 in sort of combating it. Like in Africa, they've done great work, and also mother-to-child transmission. So an HIV-infected mother, we have ways to protect the newborn child during delivery from infection. That's been very effective. So with all those things together, you really curtail the amount of new infections that we get, but we're still getting new infections. And so if we can expand these programs even further, WHO is hoping that maybe in 2030 we might be able to wipe it out. However, that is of course very positive thinking. That means we should, because we're only halfway now. And so hopefully if we can keep those efforts going, we might be able to get rid of it. However, you see now in the news, like Martin Sheen or Charlie Sheen, the actor, he's infected. And so we're not out of the woods. Also in North America, there are places, for instance in Washington, D.C., where the rates of HIV-infected individuals is 3%. And that is just as high as in Africa. So there are areas also close by to us where we get still people infected. Also in Canada, we have about 2,000 new infections every year. And we have about 75,000 individuals. Yes, the number is growing because our patients live longer thanks to good care, but we're still not out of the woods. And you still see sort of these changes in people getting infected. And there are other places in the world where actually you see the infection rates go up. So it's still a battle, and we still need to find it. The other thing is, yes, people say, oh, we have spent a lot of time and a lot of money on it. What did we learn? We learned a lot about HIV, but we also learned a lot with that work about other viruses and other infections and how our immune system works. So we learned a lot out of it. We still have a lot to learn, and the stuff what I do is really looking at how does the virus evolve and become drug resistant, where does it hide out in the body, and how does it manage to sort of escape the immune system. Those are the things I do. And I think I covered almost everything. So I would be more than willing to answer questions with regard to HIV/AIDS, but also with other things with regard to viruses or viral infections.
All right, well, that's certainly very interesting and important research that you do, Dr. Van Marle. You spoke a lot about treatment options and how HIV is best treated to at least diminish the effects. We have one question on Twitter here from Casey Daleman at Trudeau High School in Markham. And she asks simply, how does the HIV virus destroy cells? And from that question, does it matter at which stage in the mutation process we treat the individual as to how effective we can be?
Okay, so how does HIV destroy the cells? Like, you might have seen maybe some of those stories like from, the virus gets into a cell and then it starts to replicate, and in order to get out of the cell, it has to blow up the cell. That is one way of doing it. That's how some viruses does it. HIV doesn't necessarily do it like that. A living cell can keep producing virus and spitting it out. How does HIV destroy the cells? It's really interesting because HIV has many, many different ways of targeting different pathways in the cells and disrupt them. One of the things is how cells die is that it induces inflammation. You might have maybe some infection and you get this inflammation, the redness around the wound that you have. Now you have to imagine that's through your entire body. Yeah, so this inflammation, so it's basically like the virus induces a response of the body that that looks like inflammation, like it is an infection. It recognizes it, it over responds, and in the process of doing that, it starts to deregulate the cells, and they start to die faster. Because when you get an infection, the immune system makes lots of new cells, yeah, in order to fight off any infection, doesn't matter what. And then at a certain time, and if it have combated the cells, the immune system has to get rid of those cells, because otherwise your bloodstream would be, every time you get an infection, it would be filled with immune cells, and there would be no place for red blood cells and to transport oxygen. So the immune system says, there's pathways, cells die. So there's what we should call a programmed cell death. It's sort of like a program where you say, okay, these cells I don't need anymore, get rid of them, just keep a couple behind as our memory to see if the same one invader comes in again, we have that memory. So actually HIV can disrupt that pathway and make it so it induces inflammation, so your immune system starts to respond, but also starts to kill cells to turn things off. And you get basically cell death. Other things, the viral proteins of HIV are toxic to cells. So the cells actually die because it produces all these toxic HIV proteins. So that's another way of how they die. And then in that process of dying, they release molecules, regular cells, so some of them are the HIV proteins that then bind to other cells, and because they're toxic HIV proteins, those cells die, as well as it releases molecules that are normally signals for cells to die. So it's basically all miscommunication by which the cells eventually die. Now, to come back to your question about how then can we take advantages for treatment? If we would be able to, a lot of this damage to the immune system also happens during early infection. So when somebody gets infected, newly infected, you get a peak of virus replication, you feel fluish, but you don't have AIDS. Your immune system gets attacked, your immune cells die, and then it sort of goes dormant. But in the meantime, it's chewing away at your immune system the whole time to wear it out. So in theory, if I would give somebody treatment really early, I might be able to prevent that from happening and keep your immune system better at bay. Now those drugs are toxic, so they're not the best thing for you. On the other hand too, if I start you maybe too early with treatment, the virus will have a bigger chance of becoming resistant and all those other things. So it is a sort of a balance, like I want to treat early enough but not too late, because if somebody shows up with HIV AIDS, so most cases like in North America, somebody shows up, he's sick, he's immune compromised, he's got another infection, then we know not everybody gets just routinely tested so that you catch somebody early. Oh, you're HIV infected, we just keep a close eye on you, when you get sick we're going to give you drugs. So in many cases those patients show up, they're already really sick. So their immune system has gotten a real beating by the virus already. Yes, we give them the antiviral drugs, the immune system restores itself, but it doesn't restore itself to its normal levels. So treating earlier is always better. So that's why when also dealing with Africa, if we can test people early, then we know that they're HIV positive. They won't have AIDS yet, but then we can put them early enough in antiviral therapy. Yeah, so it is a balance, like treat early to protect the immune system, and maybe waiting a bit so that the virus doesn't become resistant. But we tend more to let's treat early.
Okay, very good. So that's good to know that we are making such progress on the treatment aspect of things. I guess I can sense your enthusiasm for the study that you're involved in. And I just wondered, for the students out there, what exactly was it that inspired you to become a virologist, and what advice would you have for the students wanting to get involved in such a field?
Well, how did I get some of it's just by accident, in a sense. Like there are things that pop up. Like when I went to university, HIV just was coming out. It was a new infection. It was weird. It was, and I never thought I was going to work in that area. I actually worked on viruses in plants, and I was interested in agriculture. And in those days when I started, people started like genetically engineering. That was really interesting, and we could do so much more than we could do in like before, and we were discovering all these new things, and that really got me interested. The interest in the new things that nobody else works on, or we see it all around us, but we don't know how it works. So with the viruses in the plants, I got really interested in viruses that way, because I found them extremely interesting, and also how plants actually can fight off infections in a different way than we humans do, but also very efficient. And then I got interested into animal viruses because of stuff, and then HIV research, there were opportunities there, and it sort of used expertise of things that I learned, and I found it a new challenge, and I worked on something like, I worked on HIV and how it causes neurological disease, that it actually causes dementia too. So we always talk about the immune system being destroyed, but it also infects cells in the brain, and actually can cause dementia the way you would see that in old people because of aging, but also due to Alzheimer's disease and other ways that you get neurological or dementias. And that was for me, a rather new thing. Oh, the nervous system interests me, and then got into HIV, and then working with people who worked in the HIV area, working with people in the clinic, seeing how the work that we did, how it affected patients, and how we could improve knowledge so that we could actually treat patients better and understand the diseases better. But also that got me interested in all kinds of different viruses, how viruses evolve, and how we actually live with infectious diseases. Yes, HIV causes disease. We talk about flu causes disease, but we're also infected with many, many other viruses that we learn how to live with, and actually probably help us out fighting off other viruses or bacteria. So that really got me interested into these small little pieces of genetic material, what they can do, and it's all part of the greater scheme of life, because everything around it are affected with the sea is filled with microbes, and they all work together to make actually a living planet. And if you disrupt that, then you get all kinds of issues. So your advice to me was, like, for me personally, I liked the science and the interesting thing, the novelty, the tinkering away at things, trying to chisel away at a system, trying to see how it works, and also the bigger impact of things like if you have a computer, I want to know how it works. And so you have to be interested in playing with that part. But there are also I'm the guy who works with the little molecules, but there is also people very important that looks at the bigger picture. I can invent a vaccine, but how do I bring it to everybody? That's when I need other people to help me out with. And I find that very interesting too. So one of the things is, there are many, many different ways of being involved in this type of work. And they're looking for many, many different people with different expertise. For me, it was just an interest in it. I enjoyed doing it. And, that's the main reason why I did it. But also just, don't give up. It's hard work. And you won't find the miracle answer, and so you don't have to, but there is a lot of things along the way that you learn. And another thing, and I work at the university, and I also like to teach. So I like to teach people so that they can do the things that I do, or do it even better than I do, so that you contribute that in that way to improving health, improving the way we live on this planet, engineering, solar energy, whatever. That's what interests me. So it's just an interest in science. I like that, and that's what I pursued. And then sometimes, there are some interesting opportunities popping up. Just grab it, and don't be afraid to grab the bull by the horn and just do it. I don't want to advertise certain running shoes, but just do it is their, is I think a good thing to do. Is I've got a knack for something, I'm gonna try and do that.
Yeah. Okay, well, hopefully we've convinced some of the students out there to ask critical questions about the viruses and some of the things that they hear in the news. I guess we might have time here for one more question, and today being World AIDS Day, as you said, maybe if you could comment on just the sense of, is it optimism in your field about the progress that we're making in dealing with HIV? Just maybe a sense of where, in general, the field of research is at.
Well, we've learned a lot, and we're getting to know more and more, and we're getting better and better at treating it. And if you also see that actually the things that are going on, if you read the World Health Organization reports and some of the very positive things that we see in Africa with regard to the fight against AIDS, with rolling out treatment, prevention programs, education programs. So some of those, like a prevention or an education program, has nothing necessarily to do with the science of how the virus works, It's based on the fact, like, it's not as infectious as Ebola, and you can prevent infection, and it's relatively, on paper, very easy to do. You could still have, if you get treated well and you have a good support system, you could live with the infection. If we've seen how successful we've been now so far with rolling out some of those therapies, reaching people, testing people, treating people, if we can keep that up, if the numbers, although the numbers are not really going down, we've slowed the pace quite considerably. And I think there is, a lot of education and there's a lot of awareness in those countries where that are hardest hit by this infection. I'm very optimistic. I do believe there is ways how we combat it, because there are people out there who can naturally do it. And if we can figure that out, how that works, we can use that to develop a vaccine or a treatment, and that can also be applied to other viruses, because or other infectious agents or pathogens out there, because similar rules apply to those agents too. So I'm pretty optimistic as long as we keep a concerted effort at this. Like over here, we don't hear a lot about it. You might hear it. There's a lot of, it doesn't affect me. That is probably the hardest thing, because once we lose the attention for it, I'm afraid that we're going to see it pop up back the way it was. And then we'll not be able to. It's a tricky virus, and it's a very sneaky one that hides away in nice places. Yes, in the long run, we might be able to learn how to live with it, but that's not going to be within our lifetime, and not without losing millions of people from this infection. But I'm pretty optimistic based on the things we learned when I started, what we didn't know, and now what we do know, that we're getting better at it. And also it has helped us with other things. Like if we were to Ebola outbreaks, we're way more prepared for things like that than we used to be before. And we're way better at, we learned a lot about how not to make a vaccine based on HIV, and now which might help making us vaccines for like Ebola and things much, much faster.
All right, well, that's certainly good to hear. I know, of course, it's research and science, so it's just a matter of keeping at it, and we're still learning things, so we need to keep doing what we're doing, I think, and the answers will come by themselves. So, unfortunately, I think that's all the time we have for today. So I'd like to say thank you to everyone that tuned in to the live event today, and of course to you, Dr. Van Marle, for taking the time to answer our questions and share your expertise with us today. So thank you very much for that. Just a bit of a plug for our next live event, which will be next Tuesday, December the 8th, which happens to be the Hour of Code Day. Our guest that day will be John Shillington, who is the Chief Technology Officer with Cybera in Calgary. John will be leading us through a coding event online that we hope will be the single largest Hour of Code event ever. So please do tune in and join us for that. Thank you again, Dr. Van Marle.
Thank you.
And bye for now, everyone online.
Yep. Have a good day.